Hey chemists, in this crash course we're going to review the topics that you will be expected to know for the most part in kinetics, which is all about how fast reactions occur and what chemists can do to make them faster. So if we think of just a generic reaction, let's say A plus two equivalents of B turned into some product C, how do we express how fast reactions work? Well, we use what's called a rate law. A rate law is written as the word rate equal to what's called a rate constant, which only changes with temperature and what the reaction is, times usually the concentrations of everything in the reactants of that reaction. This is called a differential rate law. And those concentrations are raised to what are called orders. These are exponents that tell us how changing the concentration of a substance in a reaction affects the rate. And you can find out what these rate laws are using what's called the method of initial rates. We'll do a sample problem like that later, but in short, it has you look at how varying the concentration initially in an experiment of one species and what it does to the rate. For example, if I double the concentration of A, does the rate double? Well, then it's first order. If I double A and this ends up quadrupling, oh, well, then this is a second order process. What if I triple this? Well, then if that triples, it's first order. If I triple this and this ends up being 9, which is the same thing as 3 squared, that is also a second order rate. It's rare that you get to things like third order, but it's possible. That would obviously be if I doubled something and the rate would be times 2 cubed, in other words, times 8. Then you would have a third order process. It's not uncommon that you have something that's independent of the rate, and you would have a zero order rate law. That would be doubling the concentration, and the rate just stays the same, gets multiplied by 1, which is 2 to the 0 power. So we'll look at some examples of how we actually solve that. The other way of getting the rate law is graphically using what are called integrated rates. And I'm going to show the 3 most common integrated rate laws we have. They are a zero order, a first order, and a second order. These are not the only ones, but they are by far the most common, and they have relationships, equations that show how concentrations change with time. A zero-order process says that the concentration of some substance is equal to whatever its initial concentration was minus the rate constant times time. First order is similar, but it's a logarithmic relationship. It's the natural log of concentration is equal to the natural log of the initial concentration minus the rate constant times time. And second order is a inverse concentration relationship. It's 1 over concentration is equal to 1 over concentration initially. This is actually plus kT. You'd see why if you went into the derivations, but that's not crucial for this level of the course. It's just important to know that those relationships exist, and most of those are given on the AP reference table. And that means that we could graphically look at relationships of concentration versus time, or the log of concentration versus time, or inverse concentration versus time, and whichever one is linear tells us which relationship it is. If it's a zero-order process, then you would have a linear relationship between concentration and time, and the others would not be linear. However, if it's first order, you would have a linear relationship between the log of concentration versus time, and the others would not be linear. If it's second order, you would have a linear relationship between inverse concentration versus time. You can tell from the equation that it would have a different looking linear relationship to be a positive slope, but it would still be the one that's linear, and the others would not be linear. That's the idea. Each of these graphically then tells you which one is the most linear, would tell you if it's if it's zero, first or second order. So that's what I mean by determining this graphically. There's also even more information hidden in these graphs. For each one, the slope is related to the rate constant. For the first 2, it's just the negative of the rate constant. For the last one, Whoops, that line actually went away, didn't it? Looks like that. The last one, the slope actually is equal to the value of k. And this is also a good time to introduce the concept of half-life. There is what's called a half-life, which is how long it takes for half of a reactant concentration to deplete. And for the zero-order case, it's a relationship of whatever your initial molarity is divided by twice the rate constant. For the first-order process, it's 0.693 divided by the rate constant. That 0.693 is just the natural log of 2. That's where that comes from. And for the second-order process, it's 1 over the rate constant times the initial concentration. It's worth mentioning only for first-order is half-life constant. And that is something that comes up a lot when students are asked to look at data related to some type of experiment and analyze some amount of data with respect to half-life. If the half-life is constant, you know it is a first-order process. That is not true for the others. They actually depend on initial concentration, so the half-life changes as the reaction goes, whereas the half-life is constant as a reaction proceeds for a first-order process. So that's just an introduction into how we represent how fast reactions work. They're with rate laws, either the more commonly seen differential or the integrated rate laws. Now, let's talk about what makes reactions faster and why. What makes reactions faster? And there's a couple of things that every chemist should know that increases the rate, always. Number one, temperature. If you increase the temperature, that makes it go faster, and that's because you're giving the particles more kinetic energy. Temperature is a measure of the average kinetic energy of particles, and if particles are reacting, that means they have to collide in what's called an effective collision, and only particles with enough energy will collide effectively to actually react with one another. You can also increase the concentration. That will increase the frequency of collisions. So that just makes them crowded, and it's more likely that effective collisions will occur if you increase the molarity of your reactants. That might also mean increasing the pressures of gaseous reactants. Remember, pressure is analogous for concentration when you're talking about things that are gaseous as opposed to aqueous, but you could think about them very similarly. Also, increasing the frequency of collisions would be increasing the surface area. This is really specific for solids. So this is specific for solids, but it's analogous to increasing the concentration and therefore the frequency as well. You're just giving them more exposure to each other. And then the fourth one I'll mention is adding a catalyst. Adding a catalyst is a very specific way of changing a chemical reaction. It decreases what's called the activation energy and gives it a new mechanism. I'll talk more about what we mean by that when we look at some sample problems. It gives it a different pathway for the reaction to occur, and it completely changes the course of the reaction, but the overall reactants turning into products stays the same. You just get a completely different path to get there, and it happens to be faster as opposed to whatever the original slow one was. Catalysts always make things go faster. In biology, they often use things called inhibitors, which do the same thing as catalysts. They give it a different path, but they intentionally slow it down. However, conceptually, it's the same concept. You change the activation energy. Inhibitors actually increase it, but otherwise they do something very similar by decreasing a reaction's pathway, or hopefully eliminating it if it's one you don't want at all. Let's just wrap up this review and do some practice problems by looking at some energy diagrams. Speaking of catalysts, if we were to plot an energy diagram like so for the energies of reactants and products versus the reaction progress, we can look at a thermochemical diagram of reactants going to products and seeing a path under which that reaction goes. This is from reactants to products. There's things here you should recognize. For example, the height difference between the reactant energy and the product energy. That is your change in H. But the height from where you start to where you max out is what the activation energy is. That's when you get up to this transition state at the top. Adding a catalyst changes the mechanism and gives it a different pathway. You automatically will get what's called an intermediate, and you'll probably have at least one intermediate with two activation energies in between. If I'm going left to right from reactants to products, I'd have an activation energy there. I'd actually have a second activation energy, this little tiny one here from the intermediate to the second activation energy, second transition state. Obviously, this is the lower activation energy compared to the original, and that's why catalysts make things go faster. Catalysts always give you a multi-level pathway as opposed to a concerted pathway. This is not to be confused with another energy diagram which doesn't show catalysts, but it shows the effect of energy of molecules. So I'll draw one more on here that shows the molecular energy versus just the fraction of collisions. And what you're going to see is what's called a Boltzmann distribution. If we have, let's say, some sample of gases at some temperature, and it has a distribution graph that looks like this, let's call it T1, and then you have some colder temperature. We saw this in the gases unit, in the gases review as well, say T2. I could plot right on top of this where the activation energy barrier is, and let's say it's arbitrarily at this vertical dashed line. And remember, these curves are representative of areas underneath the curves. So what this shows us is what fraction of molecules actually falls past this activation energy barrier. And I can tell for the hotter temperature, I have many more molecules that are outside this barrier, and they have overcome the activation energy, as opposed to what little fraction is outside that barrier. So here I have only this many molecules at the colder temperature, as opposed to this many molecules at the warmer temperature, because this is an area. It's imagining a whole lot of bar graphs right next to each other. That's what a distribution graph is. And the hotter temperature, because they have more average kinetic energy, more of them can pass the activation energy of that reaction. This kind of graph conceptually has a lot of common sense things buried inside of it. It's just important to recognize how to interpret it and possibly even how to annotate it. Okay, that's a very quick crash course in all the conceptual things and many equation-based things. Let's look at a bunch of practice questions, starting with some multiple choice and working our way to some free response questions. So first up, a chemist is studying the rate of the reaction. X plus Y2 becomes X2Y2, and the results are below. What's the rate law based on these results? This is an example of using the initial rates method, and we can do this just by inspection. You get to pick two experiments where the molarity of something stays constant and the molarity of the other thing changes, and you correspondingly look how the rate changes. So it looks like X stays the same in 1 and 2, but Y is doubled, and it looks like the rate is also doubled, so that means it's first order with respect to Y. Now let's look for a place where Y stays the same, but X changes, and how does the rate change? Well, here Y stays the same. However, X is doubled, and it looks like the rate is also doubled. So it's also first order with respect to X, which means both of the exponents are going to be 1s. So the correct answer to this, just by looking at it, should be choice A, where they are both powers of 1. Notice the orders do not match the coefficients. That's not necessarily true. When that happens, that's because usually the reaction is an elementary reaction and a concerted one that happens all in one step. But that must not be the case for this, because B would have orders that match the coefficients, and that's not the case. They're both 1. Many students might accidentally pick that because they don't realize you have to use the table. All right, right below it, here is one of those distribution energy diagrams. Exactly what we just reviewed in the crash course first slide. The diagram below shows the distribution of energies for equimolar, meaning same amounts of reactant at a different temperature. Which temperature will be the fastest? Well, I just need to find the highest temperature, and that's going to be the one that's the most spread out. But it's also because it has the greatest fraction of molecules that lie past that activation energy. So we're looking for T4. That's our hottest temperature, which really means I could just circle choice D and move on with my life, but I'll make sure the wording is correct. A large fraction of molecules have equal to or greater than the activation energy. Yes, that's true. That's your hottest one. If they asked what the slowest one would be, it must be T1. That's the coldest, and it has this tiny little fraction of molecules that overcome the activation energy. All these other amounts of molecules have energy. There's just not enough to cause an effective collision. They're just bouncing off each other, and no reaction is actually happening. Okay, moving on. Consider the decomposition of ammonia and nitrogen. The reaction was studied using 2 different initial concentrations and graphed. What is the rate law? So decomposition of ammonia, I could just think quickly about what that looks like. That's ammonia becoming nitrogen and hydrogen. A rate law is just going to depend on the reactant. It'll be 2 ammonias becomes 1 nitrogen and 3 hydrogens, but I don't know what the order is because it doesn't necessarily match the coefficient. It can't possibly be D because it's only going to depend on the reactant concentration. However, here it's concentration versus time that's linear, so this is actually a 0 order process, which means rate is equal to a rate constant times the reactant ammonia to the 0 power, which means that this term is 1. So the rate is just constant. So rate is K, and the correct answer would be A. If this showed me a logarithm on the x-axis, then I would choose the first order. If this showed 1 over molarity, I would choose the second order case. And if it was the reverse reaction, they'd give me information about that. Maybe it'd be choice D, but clearly not in this example. Here's another question that's very similar. Given these 3 different graphical relationships, what's the order with respect to this reactant? All you need to do is find the linear one. It is logarithmic. That's first order. You just have to know what these relationships are. There's the 0 order relationship, the first order, and the second order relationship. You just find the one that's linear. That's first order, and you move on. Oops. 5th question. Of the 4 elementary reactions below, which has a rate that's independent of molecular orientation? So molecular orientation refers to the fact that when molecules collide, they have to actually point toward each other in the right direction. For example, if I look at the 3rd one, I can tell that a carbon monoxide molecule picked up an oxygen to become carbon dioxide. So if I think about what those molecules look like, there's carbon monoxide, here's oxygen, and it makes a carbon dioxide. I don't really need to draw them for this, but I'm doing it for this exercise. And then an oxygen, just an oxygen atom. This one would depend on orientation because to make a CO2, I need to form a new carbon-oxygen bond. So when carbon monoxide collides with oxygen, the carbon atom has to hit one of these 2 oxygens in order for that to work. I'm not making a new OO bond, I'm making a new CO bond. So that does depend on orientation. And frankly, most reactions do that. But I can look at the first one and try and imagine, does this one depend on orientation? No, not at all. Think about 2 oxygen atoms. They just have to collide with each other. They're just like particles to make a new oxygen-oxygen bond that looks like that. So which one is independent of orientation? Must be reaction A. And as it says, the electron clouds are distributed asymmetrically, which is not true for any of the other molecules as an explanation. Maybe the electron clouds are distributed asymmetrically in other molecules, but this one is so symmetric that it's got to be the one that doesn't depend on orientation. All right, last multiple choice. The picture below, nice picture, shows the reaction of making ammonia from elemental nitrogen and hydrogen. This is done apparently on the surface of ruthenium, which weakens the triple bond, and I can tell what's happening. The nitrogen first reacts with the ruthenium to make these split nitrogen atoms. What's the role of a ruthenium atom? This is a perfect example of just what a catalyst does. This is changing some concerted reaction, exo or endo, I don't know, to some stepwise path where I have an intermediate. And this is the intermediate. It's these nitrogen and hydrogen atoms bonded to the catalyst. The catalyst is this species. The intermediate is the complex that's formed between them. And I see the intermediate in the energy diagram. It's not the crests. The crests are transition states. But the trough that's here is the intermediate, if I just had to label it. And that shows that it's a catalyst. Notice they even give me the incorrect answer of ruthenium being intermediate, and that is not the case. An intermediate would be maybe the correct answer if they asked me about an individual complex of ruthenium nitrogen, but the ruthenium atoms themselves are consumed and then regenerated. That's what a catalyst does. A catalyst, by definition, is consumed, then remade. Interestingly, an intermediate is the opposite. An intermediate is produced, it's made, and then it's consumed later on, which is true for these complexes. I make a ruthenium nitrogen complex, and then I react it, so it's the opposite of a catalyst. Okay, let's take a look at a few free response questions to wrap this up. Lots of questions in this crash course, because kinetics is a big topic on the AP test usually, but they're usually pretty quick to answer questions. The concepts are fairly straightforward. Here's an energy diagram. I can tell already they're going to want me to add to it. So consider this synthesis of HI. Delta H is negative, and here's a template of the energy change. Complete the diagram by showing a solid curve that shows the progress of the reaction in a single step. So the first thing I think they want me to make sure that I know is that this reaction is exothermic because of the negative energy. So I'm going to have some arbitrary place showing my HI product, and it is exo. It's at a lower energy. If it is a single step, that means I'm going to have a single curve separating the reactant and product. I'm going to make that a little bit smoother as I go from left to right. That's a single step. And that should be it. Now, draw a dashed line for what would be observed with a catalyst in this reaction. A catalyst should have a lower activation energy. It should start and end at the same spot, and it should have at least one dip, and I'll give it exactly one. So I'll draw a dashed line that gives me a lower dip. Usually that's the intermediate. It's never going to be as low in energy as either the reactant or product, so I'm actually intentionally keeping the intermediate at a higher state than either the reactant or product. I don't know if they would still give you credit if you drew something that was low down, but that shouldn't be true. You have to have an activation energy. Part C, draw a vertical line segment that corresponds to the activation energy of the reverse uncatalyzed reaction. So they want a vertical line that shows the height from the reverse reaction, so going this path in the uncatalyzed pathway. Very specific directions with one specific answer. I can even draw it outside the graph, and I would draw it from where I made my products to the transition state of the uncatalyzed path. And that should give me full credit on that question. Last one. Given the mechanism below, what's the overall reaction and what's the rate law? We're ending with a slightly challenging question here, and you'll see why. The overall reaction isn't too bad. You just have to add up the reactions and cancel intermediates. We have an intermediate chloride. We actually have two. that are produced and then consumed. A chloride is an intermediate, or chlorine atom, I should say, in this case. We have another intermediate, the CCl3 is also an intermediate in this reaction. And when I do that and box out what's left, it looks like I have Cl2 plus chloroform makes carbon tetrachloride and HCl. So I'm just going to write that. Cl2 plus CHCl3 gives me a CCl4 and an HCl. Easy. Now they want the rate law. For the rate law, I just have to look at the slow step, and at first glance, I write that rate law. Rate is equal to K times the concentration of everything that's a reactant in that step, which is a chlorine atom and a chloroform molecule, so Cl and CHCl3. And for a mechanism question like this, the coefficients become the orders. So if I zoom in and check, the coefficient of each of those species is 1. So the coefficient of each species is 1 in that rate law. But that is not correct. That's a good start, but that's not what earns me credit on this question. And that's because of something we said earlier. A chlorine atom is an intermediate. It's not an actual reactant. And the rate law needs to only have reactants. Rate laws can only include reactants. I'll qualify that actually, and catalysts. They can have a catalyst if there's a catalyst in the mechanism. And in fact, if there's a catalyst in the mechanism, it's almost always for sure in the rate law. Rates do depend on the concentration of catalysts. This one doesn't have a catalyst, but we do have intermediates, and we can't have the intermediate. But you don't just X it out. I've got to somehow substitute the concentration of the intermediate chlorine in terms of something else. This is called the pre-equilibrium method, and to do this, I need to go back up to the mechanism and focus on this first step, this equilibrium. And using the pre-equilibrium technique, which is the most common one we come across for doing this, you can write an equilibrium constant for that first step. Remember, equilibrium constants are the products raised to their coefficient divided by the reactant raised to their coefficient. So K is this chlorine atom squared divided by the concentration of chlorine. That means that the chlorine atom concentration is equal to the rate constant times the chlorine concentration square rooted. And now I have an expression for an intermediate in terms of a constant and a reactant. So I'm going to substitute that down below and rewrite. This is now some rate constant times, instead of chlorine, I'm going to write equilibrium constant to the 1/2 power, and then the chlorine concentration also to the 1/2 power, and then I keep my CHCl3 to the first power. And then just to make life simpler, I have a rate constant that I'm just writing as a generic rate constant for the second step. And then I have an equilibrium constant, which is really the ratio of the forward and reverse. Remember, that's actually K1 over K negative 1. But I'm just going to combine all those. This is K1, and this is buried K1 over, or actually this is K2, pardon me, and this is K1 over K negative 1 for forward and reverse. But I could just combine all that into some K expression. So I'm going to do that. I'm just going to rewrite this as K times the concentration of chlorine to the 1/2 times the concentration of the other reactant, CHCl3, to the 1. And that is the correct answer. This is an example of where we don't get whole numbers for your orders of reaction, and that's why, because we end up rewriting the rate law so that we don't have an intermediate in the overall rate law. That's a tougher question. You don't see that too often, but it's certainly fair game for the AP test. Okay, that concludes our crash course in kinetics. Hopefully that was helpful to cover some topics and go through a lot of practice questions. Thanks for watching.